In this video lecture, we're going to cover reduction and oxidation reactions, collectively known as redox reactions, and the second half of this is going to cover the role of enzymes in metabolism. Our learning outcomes today include: you want to be able to understand how reduction and oxidation reactions involve the transfer of electrons, and secondly, you want to be able to explain the role of enzymes in metabolism. Have you ever sat around a campfire and wondered what exactly is that flame? I know that Beavis here likes it. He's always into his fire. Well, in college, I learned it was a redox reaction. A redox reaction. That doesn't sound exactly exciting, but it is once you understand what a redox reaction is. First, a redox reaction is a chemical reaction. We're making and breaking bonds. You may recognize our chemical equation. This, of course, is cellular respiration, which is very similar to fire. So in the reactants, we're going to break those bonds, and we're going to form new bonds of the products. Redox reactions are like other chemical reactions. You have to have an input of energy to break the bonds of the reactants, and we call that the activation energy. So if you're like me, this is what you're going to do. So to get a fire, you got to start with some wood, and I put lots and lots of lighter fluid on there, and a match, and I strike up my fire. So, our fire is a redox reaction. What exactly does that mean? Let's get to the nuts and bolts of it now. When we look at the atomic structure of sodium and chlorine, we realize that chlorine is way more electronegative than sodium. It has 17 protons to sodium's 11 protons. So what happens is chlorine is going to snag the electron from sodium and it's going to gain a negative charge, whereas sodium is going to lose that electron and gain a positive charge. And what's happened is that as sodium has lost as an electron, it has become oxidized, and chlorine has gained the electron, so it's become reduced. The reason why we call reduction and oxidation reactions a redox reaction is because the two reactions always occur together. And that makes sense. If you're gaining electrons, somebody's losing electrons. So we call them redox reactions. Here's a good way to remember reduction and oxidation reactions. Think of Leo the lion. And in fact, the scientific name of lions is Panthera leo. And you can remember Leo says ger, where Leo means losing electrons is an oxidation. Ger is gaining electrons is a reduction. The general equation for cellular respiration, we're going to take some glucose. During cellular respiration, we're breaking down organic molecules that have a lot of carbon and hydrogen in them. And carbon and hydrogen form nonpolar covalent bonds. Recall that in a nonpolar covalent bond, you're sharing the electrons equally, which means those electrons are equidistant between the elements in the molecule. When we break them down to carbon dioxide and water, we start forming polar covalent bonds. In this case, the electrons move toward the oxygen because oxygen is more electronegative than carbon. So because the electrons moved away from the carbon has now been oxidized. As carbon is getting oxidized, oxygen is becoming reduced. And here's how it works. Molecular oxygen is one of the reactants of cellular respiration. And there's two oxygen atoms held together, and they're being held together by nonpolar covalent bonds. Yes, oxygen almost always forms polar covalent bonds, but oxygen being bonded to itself, well, they both have the same electronegativity, so they form a nonpolar covalent bond. Then during cellular respiration, what happens is those bonds are broken and then they form new bonds with the hydrogen. In this case, they're forming polar covalent bonds. And of course, they're also forming polar covalent bonds with the carbon as well and carbon dioxide. And as a result, the oxygen is now being reduced because it is gaining electrons. Let's get back to that question. We know that at fire there's energy being transformed, but what is fire? I know Beavis is interested in what fire is. We know it's a redox reaction. Well, that's not exactly the most satisfying explanation of what fire is. Let's take a closer look. We know that fire is a chemical reaction involving glucose and other organic molecules. And when we look closely at glucose, like other organic molecules, it's full of carbon and hydrogen, and we're going to react that with molecular oxygen. Now, these are the reactants, and they're full of nonpolar covalent bonds. And we can see our nonpolar covalent bonds between carbon and hydrogen and between carbon and carbon. And also, we have it between the oxygen molecule as well. During a fire, the chemical bonds of those reactants, they're being broken, and we're getting new molecules, such as carbon dioxide and water. However, these are the products, and they have polar covalent bonds, so the electrons are not being shared equally. The positions of the electrons in your molecules matter. You see, the further away an electron is from the nucleus of an atom, the more potential energy it has. So when you have lots of non-polar covalent bonds, like in carbon and hydrogen, those bonds store lots of energy. However, as we form these products, these are all polar covalent bonds. The electrons are moving closer to the oxygen, so they are losing energy. Now let's get back to the first law of thermodynamics. You can't gain or lose energy, actually. It's a conservation of energy. So the energy in the reactants must be equal to the energy in the products, and in an exergonic reaction, you're going to release some energy to the environment. So how does that work? That first law of thermodynamics, the conservation of energy, is maintained because as the electrons move closer to the oxygen atoms, they're giving off photons of light. Now, in the fire, what you're looking at in the flame, that is the carbon dioxide and water being formed, and as the electrons move closer to the oxygen, they're emitting photons, and they have enough energy that we can actually see them as light, and the ones that have a little bit less energy, we feel as heat. So redox reactions. What's the role of enzymes in all of this? Well, if you've ever started a fire, you have to add a little bit of a flame to it. That's the activation energy required to break the bonds of the reactants. However, inside of our cells, we don't have little flames we can use to light it on fire to start the reaction going. So instead, we rely on enzymes. And what enzymes do is they lower the activation energy. So they make it easier for the bonds of the reactants to be broken. Enzymes facilitate chemical reactions by lowering the activation energy. So you can take your substrate, for example, sucrose, which of course is a dimer of fructose and glucose, and we want to break that down into the individual building blocks, glucose and fructose. Well, sucrase is an enzyme that will do that, and it has an active site. Next, the enzyme is going to bind with the substrate, and it's going to slightly change shape, and it's going to form an enzyme-substrate complex. Here's one thing that is incredibly important: shape. Without the proper shape, the enzyme doesn't work, and in fact, we have unique enzymes for very specific chemical reactions. When the enzyme changes shape once the substrate binds to it, well, it also starts to change the shape of the substrate, making it easier to break the bonds holding it together. Then the products are released. And this would be an example of a catabolic reaction. We also have enzymes that facilitate anabolic reactions as well. And this simple diagram just goes to show how shape is important. We've got two different dimers, lactose and sucrose. Lactose is of course made of galactose and glucose, and it fits in lactase. However, sucrose, another simple sugar, will not work in lactase because the shapes are different. They cannot bind to the active site.